Thanks for being here with us this morning, and thanks for being patient with us too. Technology's great when it works, but we always get it eventually. I'm Katie Earle, and I'm from the Erie County Department of Senior Services, and we're here with Donna Wysokenski this morning, and we're glad to have her back. She is only on the phone, so I'm going to be clicking through her slides. She's going to tell me next when I should be moving forward, so just be patient with us for that, please, but I'll do my best to keep up with her. If you have any questions or comments, toss those right in the chat feature and we'll get to as many as we can in the time that we have today. If you're new to us, your chat is located at the lower right-hand side of your screen. If you're on a computer and if you're on a tablet or smartphone, touch your screen. That brings up your control panel. You'll see a circle with three dots and there you'll have your chat. So we hope you participate. We are recording this session and if all goes as planned, I'll be able to post it in the coming days. And quick shout out to our sponsors, which is my Department of Senior Services, Highmark Blue Cross Blue Shield of Western New York, Excelsior Orthopedics, and Wegmans for all of their support and senior services. Is it 858-8526 if you need anything? And that's a hilarious thing on your first slide. Donna, I'm just reading that now. All right, let me introduce you to everybody.
Okay.
Donna Wysokenski, MS, MA, has a variety of work experiences ranging from working on gene therapy for cystic fibrosis, she was a molecular biologist in a past life, to environmental justice and sustainability. Currently, she works at Growing Places, a great organization in Massachusetts seeking to improve the life or the health of residents through an equitable, just, and sustainable food system. So, Donna, thank you for being here with us virtually. I'm going to turn it over to you.
Okay. Hi, everybody. Please let Katie know if you can't hear me well, because we had a few tech problems, and I'm talking to you on the phone, but I would really love to see your faces too, but I can't. So today we're going to be talking about acids and bases, and this talk came about because last year I gave a talk about green cleaning to a group, and we talked a little bit about cleaners, and some of them are very strong acids and bases, and somebody wondered what that was. So here we are today talking about acids and bases as a very, very basic introduction. So acids and bases, Katie, the next slide. Acids and bases are everywhere. And so we may know that many industrial processes use acids and bases to make the things that we use every day. So in the left-hand side, you see a sulfuric acid. And sulfuric acid is used, in a lot of different kinds of processes, from paints and dyes to making man-made fibers that we might wear in our clothing, fertilizers, and purifying petroleum products. And on the other side, you see another, a strong base, which is sodium hydroxide. And this is where we talked in the previous workshop on green cleaning that some drain cleaners and oven cleaners have very strong, and you really need to be careful with them. And we're going to go over why that's a problem for us in our bodies. So then you see different kinds of acids, such as acetic acid, cupboard, known as vinegar for salad dressing. So if you ever look at a packaged food, or if you were on my green cleaning workshop and buy some safer cleaning products, you may see citric acid in the product. And citric acid is obviously found, but it also acts as a preservative in cosmetics, in some packaged food, and in some cleaning products. On the right side, you see different kinds of bases. We talked about sodium hydroxide, but potassium hydroxide is a base, and that's used in soap making. We also have a weaker base in our cupboards to make our cookies with, which is sodium bicarb, which is baking soda. And then we have magnesium hydroxide. Any of you who suffer from heartburn, you may be taking these antacid tablets, and that contains sodium hydroxide, which is going to counteract the acid that's in your stomach causing your heartburn. And then ammonia is used in agriculture. It's used to make fertilizers. It's used in some industrial things. And if you look at some of the cleaners you may have in your house, you may be using some products that either have ammonia or you may be buying ammonia. That is a base. And one thing to say is that if in some industries that use strong acids and strong safety purposes, they need to separate cabinets, because if you ever base ever reacted with a strong acid, a chemical reaction can occur that would be very dangerous. If you ever worked in industries, you would know that, and for strong bases. So I just want to make sure everybody's hearing me okay. Anything, Katie?
Sound good, Donna. Thank you.
Okay, so the next slide, Katie. So on this slide here, common characteristics of acids and bases on the left. You would want to do that, but acid part to you, and bases are going to. Strong acids are very corrosive, which means they're going to affect the metal in your car, causing corrosion. They are the things that are used for etching metal. So because they react, acids react with most metals. Bases, on the other hand, are caustic. They don't react with metals, which is why bases are used as drain cleaners. Obviously, pipes can be metal. Acids, so I wouldn't recommend you sticking your finger in a strong acid at all, but if you put your finger in vinegar, which is a weak acid that you might have in your cupboard, it's going to feel like water to you. But bases, so you want to think of like your soapy water when you wash your dishes, they're going to feel slippery. So on the right side of this slide is the pH scale. I'm going to talk about the pH scale again in the next slide, but the pH scale is a scale that measures how strong or weak an acid or a base is. And you'll see in the very middle, it's water, and water is neutral. It's very safe, and it has a pH of 7. If we go up from there in this diagram up, so as the numbers get lower and lower, we're getting to stronger and stronger acids until we get to battery acid, which is a very strong acid. Obviously, that can cause burns to you. So urine and saliva, the saliva in our mouth, that's a very weaker acid. And then some people, you know, can't drink coffee or tomato juice or orange juice because those are all acids. Soda, so we may be drinking soda, and soda has quite a acidic pH of around 3. So not only does that impact the enamel on our teeth, but soda also has a lot of sugar in it, right? So we're giving our teeth a double whammy when we are drinking soda, both with the acids and with the sugars. And then on the other side, as we go higher and higher numbers, this becomes higher and higher stronger bases. And so seawater, we obviously swim in the sea. So although it's a pH of 8, slightly basic, it's still safe for us. We eat baking soda in various baked goods. So that's another kind of base. And then you'll see that ammonia is a stronger base as soapy water. And then bleach is a very strong base with oven cleaners. And then finally, some drain cleaners. Now, in the green cleaning workshop that I gave, we have some alternatives to some of these products, so you don't have to use very strong acids or bases in what you're doing. Okay, so next slide, Katie. Katie, do you have the next slide? I can't see
Yep.
it.
It's okay. I'm there.
So that's okay. I'm like waiting for the slide to turn, and I'm so okay. So let me just go over this next thing and say to you that the pH scale, one thing about it is that it's logarithmic, and it's based on a log 10 scale. So what does a logarithmic scale mean? It in the case of the pH scale, which is a base 10 logarithm, it goes from, so a pH of, so a logarithmic base 10 scale, you can think of 1, you start at 1, then it goes to 10, the next step is 10, the next step is 100, the next step is 1,000. So very quickly, you're getting to increasing numbers with a logarithmic scale. Basically, you're taking the number and multiplying it by 10. So let's look at this pH scale. The difference between black coffee and saliva is a pH of 1, but the difference really is a 10 times difference. The difference between black coffee and orange juice goes up 2 pH scales, which means it's 10 times 10, which is 100 times stronger acidic solution. So if you look on the left here, the pH scale reflects the hydrogen ion concentration in a water-based solution. So the thing to key in on here is the hydrogen ion, that the pH scale reflects the hydrogen ion concentration, because that's what makes something more acidic or less acidic. If you look at a pH 4, again, let's see the tomato juice. It's a strong, pH 5 is a less strong acid than pH 4. So black coffee is 10 times less strong of an acid than tomato juice, which is a pH 4, because as we're going down this scale, getting towards a very strong acid, we're increasing by increments of 10 times. And again, like a pH of 12 is a 10 times stronger base than a pH of 11. And then you see water. Water is the basis of life. It's most of our body is made out of water. It's neither a strong acid nor a strong base. It's neutral, pH 7. Okay, so next slide. Before we get into a little bit of chemistry, because I realized in doing this working on this presentation, I really couldn't talk about what exactly is an acid or a base without talking a little bit about chemistry. So to define some terms, and we'll go over these terms as we go along again in this workshop. But an atom is a basic unit of matter. So on the left here, you see a diagram of a molecule, and you see those little different color balls. Those are representing different atoms. So I can tell by the structure of this molecule that it has a carbon ring to it. Those are the black atoms. So the black things are, we can say, carbon atoms. And then there's different colored atoms that may represent hydrogen or calcium or copper. Now you notice those white things that are attaching each atom to the next one. Those are representing in a visual form chemical bonds, and those are a chemical bond known as a covalent bond. So they're very strong bonds. They're holding this molecule together, and basically a molecule is 2 or more atoms, as you see here, held together by attractive forces known as chemical bonds. So the thing to note about molecules is that they have a 3D structure. They're not flat. They are a 3D structure. It all depends upon their chemistry and then the way that they work together in this molecule as a whole. So you can see that in this particular molecule, it looks like it has a ring structure. Those black rings, black atoms all around form sort of a ring. It helps to make this molecule its function. So the function of a molecule depends upon its structure. Now we'll talk a little bit about ions, and an ion is just an atom or a molecule, either one, with a net electric charge. It could either be positive or it could be a net negative charge. And then a buffer is a solution that can resist changes in a pH. So we'll talk about that towards the end of this workshop. Okay, Katie, next slide. So here we have a basic atom, and an atom is just the basic unit of matter in the universe. So an atom is composed of protons and neutrons and electrons. And the protons and the neutrons are in the center of the atom. We call it the nucleus of the atom. The electron is buzzing around the nucleus in an orbital. It's not exactly looking like this, but this is how we usually depict it. Orbitals, depending upon the complexity of the atom, whether it's iron or phosphorus or calcium, there are different sort of ways that the orbitals can look. But anyway, here is the simplest type of atom, is a hydrogen atom. And in the hydrogen atom and in all atoms, the protons and neutrons are in the center of the atom in the nucleus. The protons, importantly, have a positive charge. The neutrons have no charge at all. They're found in the center, and the protons and the neutrons have a weight. Even though it's very, 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 very small, scientists can measure the weight of a proton and neutron, and that makes up the atomic weight of the atom. Electrons have a negative charge, and they're found in these orbitals buzzing around the nucleus, around the positive charge, and they have very little mass. So if you look on the right here, you see hydrogen as the simplest atom. It only has one proton, one electron buzzing around in an orbital, and 0 neutrons. Most other more complex atoms will have neutrons to their nucleus. So, okay, does anybody have any questions so far?
I'm not seeing anything in the chat, but feel free to put your questions in. I'm just blown away by all these terms I haven't heard in years. So thank you,
I
Donna.
know. So I'm hoping I'm doing this so you all can keep pace. Okay, so now let's look at the next slide, Katie. Here we just talked about the hydrogen atom on the left, simplest type of atom we can have. Now, if we got rid of that electron, we end up with just the hydrogen ion. And so remember that we said that an ion is an atom or a molecule with a net electric charge. So in the case of the hydrogen ion, which is, the simplest kind of ion you can have, if you take away that electron, basically what you're left with is a proton, right? So if I say a proton, or if I say a hydrogen ion, or if I use the symbol for hydrogen, which is H, and I say H+, it all means the same thing. So a hydrogen ion is H+. It has one positive charge because it's just a lonely little proton. So it's one proton and 0 neutrons. Doesn't have its electron anymore, so it has a net positive charge of +1. So the thing to remember here is a proton, a hydrogen ion, and H+ all mean the same thing. So let's go to the next slide, Katie. So basically here in an ion can be, as we said, positively charged. It could look like the hydrogen ion, H+, or it could be negatively charged like the hydroxide ion, which is OH negative, which stands for oxygen and hydrogen, and it's a negatively charged ion. So if on the right you look here, a very strong acid is hydrogen chloride. And when hydrogen chloride is put in a solution of water, it immediately dissociates into the hydrogen ion, which is H+, and the chloride ion, which is Cl negative. So there's two different charges of ions, plus and minus. A strong base like sodium hydroxide, if you put that in water, it immediately dissociates, and in the solution you're going to have sodium ions, which are positively charged, and hydroxide ions, which are negatively charged. Okay, Katie, next. So here's what you want to remember. And this is sort of a definition for an acid and base, which is why we went through this whole thing. An acid is a proton donor, and a base is a proton acceptor. So an acid is going to accept donate a H+, and a base is going to accept the H+. So let's look at water. Water can act as both an acid and a base. So this is the way we generally write a chemical equation you see here. We have the reactants on the left side of the equation and the products on the right side of the equation. So if we look at these two water molecules on the left, you're going to see that the one water molecule is going to donate its hydrogen to the second water molecule, which is going to accept it. So in this case, the first water molecule on the left is acting as an acid. It's donating a hydrogen to the other water molecule, which is accepting it. So it's a base. And what you have at the right side of this equation and what you're ending up with is when this one water molecule loses its hydrogen, it just has OH left, and it's an ion now, a hydroxide ion. And when that other water molecule accepts the hydrogen, it turns into a hydronium ion, and it's a positively charged ion. So in this way, water can act as both an acid and a base. Now you note that in this equation, I wrote this purposely, this arrow in a certain way, and that is, you notice that the stronger arrow is going to the left and the weaker arrow is going to the right. And this typifies the way that this reaction happens. It's that very, 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 very little of the water in your glass of water that you've gotten from the tap. Very few of those water molecules actually do this. In fact, there's 500 million times more actual H2O molecules in your glass of water than there is hydroxide or hydronium ions. So we said that pure water is pH neutral, right? So that means that it has neither an overall positive or negative charge. So what this actually means is that every time a water molecule donates a proton, like you see here in this equation, another one is accepting it. So that the concentrations of this hydroxide ion and this hydronium ion are always equal, which makes it a neutral solution. In acidic solutions, you're going to have a lot more of this hydronium ion. That's what makes an acid solution an acid, or you may have much less. So this is important to know, is that pure water is neutral. So you can, next time you take a drink of water, you can look at your glass of water and say, there's 500 million times more water molecules than there are hydroxide and hydronium ions that I'm drinking in this glass of water, which I'm sure you can impress your friends and family with. Okay, so next slide. Okay, so just again to remember, an acid is a proton donor, a base is a proton acceptor. This means that acids release hydrogen ions or protons. Basically, they're donating hydrogen ions. Bases remove, you can think of them as removing hydrogen ions or protons from a solution, or you can think of them as accepting the hydrogen ions that are being donated by the acid. And so just remembering that when you think of a pH scale, you may take a cleaning, often cleaning products don't put this on their label, but some do, and some will say it's pH neutral. So now you're going to know what pH neutral means. If that number is less than 7, you're going to know that it is an acidic solution, and if it's greater than 7, going 8, 9, 10, 11, that means it's a basic solution. And that pH scale, that number reflects the hydrogen ion concentration in this water-based solution that you may have. Okay, so let me see. A little bit more chemistry, and then we're going to go into a little bit of how acids and bases relate to everyday life. So I thought it was important to talk about what is a strong acid and a weak acid or base. So here in this slide, you see that strong acids and bases completely ionize in solution. And we've been talking about that throughout these slides. We've said that HCl, hydrochloric acid, in a solution of water, as you see in the left here, will dissociate into the hydronium ion. So HCl is acting as the acid, water is acting as the base and accepting the hydrogen ion that the acid is donating. And on the right, the products become the hydronium ion and the chloride ion. What you notice in this in this reaction is that this arrow goes completely to the right. This means that it's dissociating completely. The minute that you put HCl, a strong acid, any strong acid, into water, it's completely dissociating into these ions. So again, some toilet bowl cleaners use HCl. They can have a very acidic pH of 1 to 3. And if you look on the right side of this equation, the same thing with a strong base like sodium hydroxide, which is found in some drain cleaners and oven cleaners. The reaction in water goes completely to the right, and all you're left with is sodium ions and hydroxide ions in solution. Now, this is different than a weak acid like vinegar or acetic acid. So this chemical formula there on the left, where you see weak acid, that's actually the chemical formula of acetic acid. And Katie, I don't know if you have a pointer, but the H that's after the 2 O's, that's the H that's going to be donated by this weak acid to the water molecule that's acting as a base. It's accepting that hydrogen, and then at the end of the solution, you're getting the acetate negative ion and the hydronium ion. And you see here that this equation arrow is in red. It's like going both ways. That's what typifies a weaker acid or base, is that this whole weak acid is not going all the way to the right. Some of it is now forming, those products on the left, the acetate and hydronium ion, are reforming to form acetic acid in the solution. So unlike a strong acid where you're getting all this hydronium ion, which is basically all the H plus is becoming in solution, here that's not happening in a weak acid. So the pH is going to be different then, because you're not having as much H plus in that solution. Now, in a weak base, that's the same thing. Ammonia is a weak base. Now, you remember that bases are accepting the hydrogen ion. So this water molecule now is acting as the acid, donating its hydrogen to this ammonia. And so in a solution of ammonia with water, what's really happening is you're getting the ammonium hydrogen positively charged ion and a hydroxide ion. And you see again that this arrow goes both ways, so that this is like forming and then reforming, going back to the left and then forming. Not everything is happening where this ammonia is completely, the reaction is going one way to the right. And again, ammonia is found in many different kinds of cleaning products. Okay, last little chemistry thing here. I said to you that if you work in an industry that has a lot of strong acids and bases, they keep these in separate cabinets, and there's a reason for that, is you never ever want to mix a strong acid with a strong base because a violent chemical reaction occurs that can release toxic gases, and it produces a lot of heat. So sometimes in some industrial accidents, this is what could be happening. And when fires happen in certain industries, this is what firefighters have to be careful with. This is why in firefighting, firefighters have to know what kind of chemicals this plant has in it, because if a fire ever erupted, they have to know what's in it. And then, again, I want to say this because a lot of people use bleach. And bleach is not your naive little chemical here. It's a rather strong base, and you should never mix bleach with any other chemical, including vinegar, including anything, not anything I can say. So sodium hypochlorite is another name for bleach, and you see what it looks like here on the left, NaOCl. And if it ever reacted, I don't know why it would, but if there was an accident and it interacted with a strong acid like hydrogen chloride, at the very end of this reaction process, what's going to be emitted is chlorine gas, sodium chloride, which is salt, and water. Chlorine gas is what was used to gas soldiers in World War II and kill them. So this is why it's very dangerous. And it doesn't have to be a strong acid. It could be vinegar. It could be urine. It could be anything that we mentioned is an acid. Bleach will react with acids. That's why you never want to mix it with any kind of chemical. Same thing with a weak base or any kind of base. Sodium bleach will react with ammonia, which is why you should never mix those two together, and it will form chloramine gas, which is toxic. So again, the rule of thumb is never ever mix bleach with anything else besides water. You can dilute bleach with water. Water is neutral, but not with anything else. Okay, so now we're getting to the more life things, things that are more common in our life, but I'm going to stop here and just ask if there's a question in the crowd.
Thank you, Donna. We did have one question that came through. If ammonia is a weak base, how can the fumes be so bad?
Yes, thank you for asking that. So ammonia fumes can trigger, as I said in the green cleaning workshop, it can trigger an asthma attack. So the fumes of ammonia can react with our lungs. Not only is some asthma, people that have asthma or chronic obstructive heart disease, those things, but it can react with your lung cells and actually interfere with it that way that they work. Off my head, I don't remember what's actually happening, but it reacts with the cells in your lung, causing your fluid to build up in your lungs. So you don't want that to happen. And thank you for reminding me to say that, whoever asked that question, is that if you have asthma or if you have chronic obstructive heart disease or any other kind of lung condition, really you shouldn't be using this ammonia because those strong fumes not only can trigger an asthma attack, but they can, you're breathing it in, it's affecting your esophagus cells in your lung cells, and it can create problems within the alveoli of your lungs, which is what the surface area in your lungs, which you need to trade oxygen and carbon dioxide. So I hope that answers that question.
I think it does. Thanks, Donna.
Okay, so here we are now. We're going to be talking about ecology, cooking, and gardening, and our blood system. So first we're going to start with hydrangeas. My sister told me start with something simple, So I'm starting with hydrangea. So any of you who are gardeners and you love hydrangeas, you may already know this, but you can affect the color of your hydrangea by making your soil a little more acidic or a little more basic. So if you want a blue or purpley hydrangea, you need acidic soil, which is around a pH of 5.5 or lower. But you don't want to get too low because you're going to kill your plant. But basically, you want the blue color, you want more acidic pH. If you want this purple, pinker color, then you want to move towards an alkaline soil. And by the way, alkaline means the same thing as basic. So when you say alkaline, it means a basic soil. So you may want your soil to be a pH of 6.5 or higher. And then if you want this sort of in-between kind of color, you want the pH to be between 5.5 and 6.5. So why is this happening? The pH indirectly affects the color of hydrangeas because what soil chemistry, if you understand soil chemistry, kudos to you because it's very complex. And what's really happening as the pH of the soil changes is that the ions in the soil, there's copper ions, different ions, iron, magnesium ions in the soil. And aluminum is one of those ions. And so what you're doing actually is mobilizing the aluminum ion in solution as you change the pH of the soil. So with an acidic soil, more aluminum becomes available to the plant, and there are pigments in the plant that when they interact with the aluminum turn the flower more blue. And likewise, when you're in a more basic soil, aluminum isn't mobilized. It remains bound to the soil particles. Less is available for the plant. And so then in the biology of the plant, the color of the plant becomes pink. So that's really cool because you can use your plants actually as an indicator of the acidity or of your soil. So that's hydrangeas. So the next thing I'd like to talk about, and that's the next slide, Katie, is cooking. So ceviche, anybody ever heard of that? You can, instead of cooking fish in the oven, you could actually cook fish. This is a certain kind of recipe, and you have to know what you're doing with it, but you can actually cook fish with lemon and lime juice because they're acids. And what's happening there, we're going to talk a little bit more about this, but acids are going to denature the fish protein and basically cook the fish. And what I mean by denaturing is that proteins are very complex. They're very 3D structures, as we talked about earlier in the slides. And the acids begin to unravel that protein structure. And this is actually what's happening when you cook an egg, right? When you fry an egg, you notice that obviously it's changing and the clear stuff becomes white. Well, that is like a reaction, a chemical reaction that's occurring there, and you can never make the egg white back to what it was, right? It's a kind of a permanent thing. And this is what's happening when you're denaturing the proteins in fish with acid. Basically, I'm going to say to you that this is why acids are not good for us, because we're made out of proteins. So strong acids do the same thing to us. But let's say you're in a grocery aisle and now you're looking at the meat, and all the prices, as you know, have gone up exponentially, and you are looking at this tougher cut of meat that's cheaper. Well, don't despair, because you can marinate that tougher cut of meat with acidic liquids. And what you're doing there actually is denaturing or unraveling these proteins in the meat and tenderizing the meat. So again, I'm not a cooking expert, and there's a certain way you can do this, because if you do it too long, you're going to make that's not going to be too good for the taste of the meat. So you want to know how long you should be marinating your tougher cut of meat, but basically you don't need to buy the expensive cut if you marinate it. And then how our base is used in cooking. So here we have this lovely looking chocolate chip cookie. And when you make a chocolate chip cookie or other baking things, you're going to combine baking soda, which we said was a base, with whatever's in your batter, but a piece of that is some piece of that is likely to be acidic. It could be either yogurt, buttermilk, lemon juice, or something else. And what's happening there is a chemical reaction where the baking soda is reacting with the acid and forming carbon dioxide gas, which is what's making your batter or your dough rise. So that's pretty cool. Chemistry and cooking. Toothpaste. So this I never thought of until my dental hygienist mentioned it to me. But toothpaste, if you look at your own toothpaste and the label, you might see baking soda in it. Toothpaste is a base. It's a weak base. Why is that? Well, remember when we talked about the pH scale and I told you that soda has a pH of 3? Well, tooth enamel starts breaking down at a pH of about 5.5. And sugar also reacts with the bacteria in our mouth, in the plaque in our teeth, and produces acids as they use the sugar for their own life. So both of those things are going to be eroding your tooth enamel. Acidic foods and drinks, so like lots of orange juice if you happen to be drinking that, or I don't know, lemonade or things like that, they can also erode our tooth enamel. So here's something interesting that I learned, is that brushing right after eating can cause some of your enamel to be brushed away, and you want to wait 1 hour before brushing. And you remember your saliva is a pH of around 6. So it's a little more towards neutral than what tooth enamel starts breaking down in, which is 5.5. So for life, these little tenths of a difference in pH make a big difference because remember we said it's a pH scale. And so your toothpaste now is a base. Now I want to talk a little bit about ocean acidification. So we're going into how acids and bases have anything to do with ecology and ecosystems. So how many of you you can think of, I can't see you, but love to eat crabs or mussels or oysters? These are all shellfish in the ocean, and their shells are formed from calcium and carbonate. And their shells are made out of calcium carbonate then. And what the marine creatures do in the water is gather calcium ions that are floating around in the water and carbonate ions floating around in the water. One is positively charged, one is negatively charged. And in their bodies, they have a reaction that produces the calcium carbonate to make their shells. Now, if there's a lot of carbon dioxide, as it is, being released into the atmosphere now with global warming from cars and smokestacks, et cetera, the ocean starts absorbing this increasing amount of carbon dioxide from human activity. And the carbon dioxide, through wave action, becomes part of the seawater, because as the wave action happens, some of the atmospheric carbon dioxide becomes into the sea. And when carbon dioxide and seawater combine, they form carbonic acid. This carbonic acid breaks down very quickly into our famous H+ ion and bicarbonate. But here's the problem. The carbonate that those shellfish need to bind with calcium to make their shells, well, this carbonate ion, it's just the way the chemistry works, binds more easily with hydrogen ion than with the calcium ion. So what's happening basically in the ocean as it becomes more acidified is that the hydrogen ion essentially is capturing the carbonate ion that the sea creatures need to make their shells, and less becomes available to the creatures to bind with the calcium to make the calcium carbonate for their shells. So that's what's happening with ocean acidification. Now, Katie, I have a little video from you that shows this. And Katie, I don't know, you can try it out. And if it doesn't work, we'll go on.
All right, let's see here. It's letting me click on it, so that's a good sign potentially. You know what, Donna? Okay, let's try it here. Let's see if
Okay.
everybody can hear it. I'm not sure if you can hear it, but it is playing.
Ocean acidification is caused by carbon dioxide emissions. It threatens the health of our oceans and the animals in it. Let's start by looking at the formation of shells in animals. The shells of animals, like crabs, are formed primarily of calcium carbonate. Calcium carbonate is formed when calcium ions bind with carbonate.
Oops, sorry. I apologize for that. I tried to mute myself and that changed it up, so we'll try it again. Can you hear it though?
Okay.
Ocean acidification is caused by carbon dioxide emissions. It threatens the health of our oceans and the animals in it. Let's start by looking at the formation of shells in animals. The shells of animals, like crabs, are formed primarily of calcium carbonate. Calcium carbonate is formed when calcium ions bind with carbonate molecules. Ocean acidification begins with CO2 emissions. Most CO2 is produced when fossil fuels are burned for industrial and automotive purposes. Once in the air, CO2 is absorbed into the ocean through wave action. Once absorbed into the ocean, CO2 combines with water to form carbonic acid. Carbonic acid breaks down easily into bicarbonate molecules and hydrogen ions. Calcium and bicarbonate cannot bind together to form shells. Carbonate that usually forms shells binds more easily with the hydrogen ions. This makes them unable to form shells. Let's review. In a normal ocean, carbonate is taken from the water and combined with calcium to form the shells of many animals. In an acidic ocean, abundant hydrogen ions bind with carbonate and prevent shell formation. Animals, like these crabs and those that depend on them for food, may eventually disappear if they cannot easily form their shells.
Okay.
Yep. Okay. So, Katie, we need to go to the next slide. And what I found is I had to hit escape a couple of times, got me back into my other view, and then I would pick the following slide.
Okay, we should be good. Effects of ocean acidification, right?
Yes, yes.
All right,
So,
we're there.
Okay, so I hope you guys can stay on for a few more, maybe 10 more minutes. I know we're supposed to end at 11:30, but so the effects of ocean acidification. The marine organisms are unable to build their shells, so we're not able to eat seafood, but it's not all about us, right? So it critically impacts the marine food chain because there are small organisms with shells, marine pteropods, and this is the basis of a marine food chain. These are the little organisms that are eaten by bigger organisms that are eaten by bigger organisms. So by disrupting the marine pteropods, we're disrupting an entire food chain. And it also impacts ecosystems such as coral reefs, which are highly diverse. They are home to a great variety of marine life. So that is very important to us, and we'll see that in the next slide too. And even now, oyster hatcheries in the northwest of the Pacific Ocean have been impacted by ocean acidification. So it's happening already now. So next slide, Katie. Oh, is that right? No, I forgot. Let's go back to the ocean acidification one. That's important. What I wanted to say here is that because it's so diverse, the marine life, scientists are finding that these very diverse coral reefs actually have become the medicine cabinets of the 21st century. So with the diversity of life they have like looked at these organisms and how these organisms solve their own problems and have found new medicines to help treat cancer, leukemias, lymphoma and skin cancers, arthritis, bacterial infections, viral infections, Alzheimer's, heart disease. So something that we never think of is like we're driving our car, we're increasing, the carbon, but we're also impacting so much more. So that's just the point that I kind of wanted to get across. Okay, next slide. All righty, folks, like I told you about protein denaturation, and on the left side, you see what happens when proteins are denatured. As we go from stage 4, 3, 2, and 1, this protein, which is very complex, is beginning to lose its structure in an acidic or basic environment. And what's happening is that some of this 3D structure not only is held together by these strong chemical bonds called covalent bonds, but they're also held together by weaker, but if there's a lot of them, it's pretty strong, hydrogen bonds. And as we apply, as these proteins are in an acidic or basic environment, they begin to change shape. So here are some proteins that are functional in our body. Our whole body is basically a proteins. Digestive enzymes help us break down food. Transport. So, for example, they're carrying substances around through our blood and our lymph nodes. An example is hemoglobin. Hormones like insulin or the growth hormones, those are proteins. Defense molecules that are immunoglobulins, are antibodies. These are proteins. So the key point here is that protein structure is very important for their function. And once we begin to add an acid or bases, they begin to denature proteins and disrupt their ability to function. So this usually happens between a pH of 2.2 to 5 or pH 10 or higher in some cases. This is why strong acids and strong bases are unhealthy for us in different ways because it's denaturing proteins and we can't get it back. Okay, that damages our proteins, and our body has to like make new ones, or we may die from that. So let's go on to the next thing. And way in the beginning, we talked about buffers, and we said that buffers sort of help to keep the pH stable. Now, buffers are really important in our own bodies because, like, think of it as acting like a sponge. In a sense, this buffer is a sponge that's releasing hydrogen ions when they need to be released or absorbing extra hydrogen ions as is needed. So they can help within a certain pH range. Obviously, they can't function without this certain pH range, but they can help to create a system where the pH range is kept within a very narrow pH range, like within 1/10 of a pH range. So that's very important to biological systems so that can maintain the pH needed for life. And so I'm going to go on to the next slide, Katie, and talk about this is the next 2 slides, and then we're finished. The bicarbonate system in the blood. So because we, in our life, I don't know if you want to close your eyes and think to yourself that thousands of chemical reactions are happening in your body as we listen to this webinar and I talk to you. And most of those are being mediated by proteins, very specialized transport proteins, et cetera. In our blood, we need to maintain a narrow pH range between 7.35 and 7.45, and this is maintained by the bicarbonate buffer system in our blood. So take a look at the bottom equation and notice carbonic acid. If you look at carbonic acid, you will see that's in the middle of the equation. Now, let's say we had too much hydrogen, H plus, on the right side of this equation. Let's say our blood became a little bit too acidic, okay? If our blood became a little too acidic, the H plus is going to combine with the bicarbonate and form carbonic acid in the middle there. and then we're going to breathe it out as carbon dioxide and water. So in this way, this bicarbonate buffer system is maintaining our pH because it's accepting these extra hydrogen ions, and then we're releasing them in our lungs, so we're breathing it out in as carbon dioxide and water. And the reverse is true. If it's too much, if we don't have enough hydrogen ion in the blood, then the reverse will happen, and we'll get more hydrogen ions in our blood. So this is a very complex system in our blood, and it also happens within our kidneys. So Katie, go to the next slide, and this is the last slide. And I'm going to tell you something that happened to me which describes this. Many decades ago, I went with some friends to Darien Lake, and I went with them on a ride similar to the one you see above, turning very fast. And then from there, we went to something like a roller coaster, up and down, up and down, up and down. And at the end of it, boy, did I feel sick. And I couldn't catch my breath. It was actually scaring me. Basically, I had respiratory alkalosis. I was hyperventilating. This is when the pH of my blood becomes too basic, and it's caused by excessively deep breathing, and I'm exhaling too much carbon dioxide. So that's why when you hyperventilate, they tell you to breathe in a paper bag, because now you're breathing your own CO2, and as you see in this equation, you're moving the reaction towards more acidity. So your blood is too basic, and you want more hydrogen ions in your blood, so you're breathing in this paper bag, and you're basically breathing some more of your CO2, and you're putting your blood pH back to normal by this bicarbonate system. The carbonic acid is moving to the right of this equation, and you're forming a few more hydrogen ions in your bloodstream to make it more normal. So that's just my own personal example of acids and bases, and they did give me a paper bag to breathe in there. So that's the end of this workshop, and I want to thank you so much, all of you, for listening. I'm happy to answer some questions, and if I know the answer, I can share it with you. So thank you again.
Donna, thank you so much for putting that together in such a simple and digestible way to understand all that information. That was awesome.
Oh, great. I'm glad that you liked it. It was just, I'm hoping everybody else got something out of it and enjoyed it, and it was clear.
Oh, yep. And I'm seeing a couple thank yous. I know we're at time. Do you have a couple minutes to just take some questions?
Sure, I do.
Okay. All right. So this first question came a little bit of a while ago. Is using bleach in the toilet bowl bad?
Okay, so, I myself, me personally, don't use bleach in, I don't use bleach at all. So I don't know, Katie, can you just share that green cleaning booklet still with people?
Yep. I can look up that link real quick.
Okay, so if you guys would like to learn more about green cleaning where you're not using strong acids and bases, Katie will provide a link to the booklet that you can download and have these recipes. But anyways, that's a good question, and thank you for asking it. So first of all, when you're using bleach or any kind of chemical, a cleaning chemical, you need to remember to use the directions, because I know a lot of people just dump some in. So that's one thing. You don't need to use more than you need to. Putting bleach in the toilet bowl is not necessarily bad. I mean, you're inhaling some of these fumes. You want to make sure it doesn't splash on you. You want to make sure that the toilet is flushed first, so there's no urine in there. You want to put as little as you need in there. But I can say to you that you don't necessarily need to use bleach in your toilet bowl. That actually I clean my toilet bowl with baking soda and vinegar. So that's a weak acid and a weak base, and that's how I clean my toilet bowl, and sometimes I might add after that some soapy. I use Dr. Bronner's soap, and I put a little bit in there, and I also scrubbed around with soapy water. So that's my technique. So I can say to the person who asked it, it's not necessarily bad, but I guess follow those directions. Don't add more than you need to. Don't try and don't breathe it in if you can avoid it. Open the window when you're using it. Don't let it splash on you. But again, there are alternatives that are safer.
All right, thanks, Donna. And I just put the link into that Green and Clean book that she mentioned. That's in the chat if you want to access that. And that rhymes. Okay, so I'm saying thank you very much. Thank you for simplifying this complex topic. I've got the chemistry and cooking was very interesting. And then I have learned so much today. Thank you very much. So Donna,
Lovely.
wonderful.
Lovely. I'm glad to have met you all virtually. And Katie, thank you so much for all your help at the beginning there with our technical problems.
Absolutely. We never give up here at University Express. Everyone, thank you for joining us. Donna, thank you. I will give you a call in a moment to debrief.
Okay. Sounds great, Katie. Thank you so much.
Bye, everyone.
Bye.